Hi everybody, I'm Janni, a physics student from Finland. I've just finished my summer internship here at the Jülich Research Center in Germany, sponsored by PRACE, the Partnership for Advanced Computing in Europe. In this video, I'll talk about how supercomputers are used to simulate electrical properties in graphene. For those of you who haven't heard about it already, I'll just say that graphene is a 2D material made of a single layer of carbon atoms in this kind of honeycomb lattice. It has some amazing electronic, dynamic, and thermal properties, but since I don't really have time to go into all of that today, you can just Google it if you're interested to learn more. Anyway, here at the Jülich Supercomputing Center, my supervisor Stefan Krieg and others have been simulating graphene lattices using hybrid Monte Carlo methods. The idea there is that we take a starting point, some kind of graphene lattice, let's say with 6 carbon atoms, and we place some electrons, say here, here, and here. We then use a random number generator to pick new positions for the electrons, some time interval, say a millisecond later. We compare the two lattices and calculate how likely the transition from one to the other would be. Let's say we find that there's a 17% chance of this happening. We then take another random number between 0 and 100, and if that number is less than 17, we accept this new configuration and add it to our trajectory. If it's going to be more, we need to reject the trajectory and try to generate a new one. Sounds simple enough, right? So why would we need supercomputers if all that we really need to do is pick numbers between 0 and 100? I mean, even I could do that with some kind of very big elaborate die. Well, it turns out that calculating the probability of a transition is really tricky. We need to use quantum field theory, basically considering all the possible paths that the electrons could take from this state to this one. And then we need to normalize this against all the possible physical outcomes. So, to put it short, there is a lot of math involved. As it turns out, the most expensive calculation that needs to be repeated over and over again is a matrix equation, the kind you might have solved during your high school math courses, for example. The matrix we're considering is called M-dagger, where M is the fermion matrix. Then there's this unknown vector x and a known right-hand side that we're going to call B for now. And as it turns out, for any kind of physically interesting Monte Carlo simulations, we're going to need to solve this equation over and over again for a different B every time. During that high school course, you might have done this by finding the inverse of the matrix. But for these kinds of big systems, that's not actually possible. Instead, different iterative solvers are used. I've mostly been looking at the conjugate gradient method, but really the idea behind any iterative solver is pretty similar. We take a guess for the vector x, multiply it by our matrix, and subtract the known right-hand side. We then look at this difference, and if it's small enough, well, then our guess for x is pretty good. But if it's pretty large, we make some kind of adjustment to x and then calculate this difference again to see if we've done any better. If we don't have some kind of very strange, crazy matrix, after some number of iterations, hopefully we're going to have a good enough guess for x that we can all agree is close enough to the actual solution. Fortunately for us, computers are actually pretty good at multiplying vectors by large matrices. So by using a supercomputer, it's actually perfectly reasonable to make some guesses for x and then multiply those by our matrix and then just subtract this right-hand side that we already know. So that's why iterative solvers are pretty good for our purposes here. Of course, if we can still make this somehow faster, then we're going to be able to do a lot more updates and therefore make these simulations for much larger systems, which is obviously really interesting. That's why over this summer project, I've been developing the so-called eigenconjugate gradient method, which adds a bit of a boost to the normal conjugate gradient method, and therefore it should also allow us to make simulations for larger and therefore more realistic graphene lattices. So that's it for my video today. Thanks very much for watching. And if you're interested in learning more, I highly recommend checking out the Summer of HPC website, where you can read more about everyone's projects from their blogs and maybe find out more if you're thinking of applying yourself next year. Thanks.